Our next speaker is Professor Markus Buehler. Many of you have worked with him, as you can imagine. Professor Buehler is a professor of engineering in both civil and environmental engineering and mechanical engineering. Today, he's going to discuss some new AI architecture driving the breakthroughs both in science and in real-life applications. Let's welcome Professor Buehler.
Yes. Well, thank you so much. Really great event, and nice to see so many of you. So I'll be talking really about how we build AI for scientific applications, and where we are today, and building AI that can think and make predictions that are not obvious, maybe discover new things. So where we're today, we've seen a lot, probably in the presentations the last day or so, about machine learning. We can train complex functions. We can even generate new data, code, sequences, and things like this. But the real challenge really is, how do we really create something absolutely new? Things we haven't had before, things that aren't in the training data. And that's what the presentation will be about. We refer to this as broadly reasoning models, agentic AI that can take actions with the world and interact with the world and make decisions that hopefully bring us forward. So that's what the presentation will be about. And my research deals, as you've seen, with materials. I study materials. These are really interesting systems. So how many of you work on materials? Not everyone. Some, yes, great, awesome. But you all, of course, know about materials. So you can look at anything, fabric in your clothing, and if you take a microscope, it will ultimately look like an atom, a molecule. And you can imagine it's a very challenging problem. Economically very important, because everything's made from materials. Even if you're not making materials, you're relying on materials, obviously. And the challenge a lot of times is, how do we design these systems? How do we understand them? And there's a lot of relationships across scales. Now, for I would say 50 years, 70 years since the 1950s, really, since we had bigger computers, what physicists, scientists, chemists did, we broke down the problem in different scales. We said, okay, we have a chemical scale, we have a molecular scale, a continuum scale for engineers, and we kind of try to bootstrap our way out of these systems. Now, what the problem with this is that, first of all, the complexity is very large. The other thing is that many of these problems across scales cannot be captured. So if you're in the protein business or chemistry business, if you're ignoring some of the details in your sequence that matters for a disease, you're not going to capture how the organism, the human, will respond to it in drug design and things like this. So this idea of sort of coarse graining and simplifying things really doesn't work. And in fact, that's sort of the road we've been hitting for a couple of decades. Now, AI has potential for us to change this game, change the equations here. And something that I think is happening, as you've all seen, we have better models, even though these models they look kind of impressive, but most of these models are still pretty simplistic and primitive, actually. And especially, even though, of course, today's ChatGPT is here, frontier models that aren't released yet are all the way up there, but still, a lot of these models aren't really able to produce new things. And you can see this if you're interacting with these models, right? And you ask them something totally new. They really just interpret a lot of times between what they've seen in the data. And this is shown here, right? So if you look at AI today, machine learning, you're really limited to the kinds of things the model has seen. Maybe you can interpolate and combine things here and there, but you really cannot go to those white spaces where you have never seen any data. And that's, of course, what we want to do. As scientists, we want to engineer, discover things, and create insights and knowledge of systems that we have never studied. And that's what we're trying to build. And so this, can be done. And I think we've made a lot of progress in the last couple of years to do this by really thinking about, how do we actually train AI? How do we teach these models? And in conventional learning, you teach models examples, and they remember these examples, and they produce sort of new combinations of examples in the solutions. What we got to do, though, to have models really understand, like scientists do, like engineers do, we have to sort of go one level deeper and understand principles. And this is what's shown on the right-hand side. So for many years in my group, we've worked on something called category theory. It's a branch of mathematics that really deals with relationships. So that looks at the world not as a collection of facts, but as relationships, and relationships between relationships and abstractions. And this is how we understand the world. So if you're asked to design something new, you're not just copying something, you're thinking about how this might relate to the problem you're trying to solve, how you combine new ideas. And so you do compositional reasoning, really breaking it down and synthesizing something new. So this is in a nutshell, what we're trying to build and teach AI models to do. Now, the question is, how do we do it and why? Well, here's an obvious example, right? So current AI models really look like sort of thing on the left. So they remember, they look at an apple falling and they say, oh yeah, it falls pretty fast. They look at a feather, they might say, yeah, it falls pretty slow. And they might look at a different problem, like dropping a glass and it shatters. Okay, well, the AI can remember this and it can give you answers. But we know in physics, there's actually all of these problems, there's an underlying theory, which is Newton's laws in this case. And you can actually describe all of these phenomena and many more by knowing this fundamental theory, right? And so now you have a true understanding and you can make predictions. And this is what really the limitations of AI are today. You can't make these kind of fundamental predictions. So in category theory, and this is how this looks like, so we've done this work about 10, 15 years ago. It's mathematics on piece of paper of a system you understand, and you can kind of write down how things relate. So on the left, you have spider silk, a protein, and on the right, you have music. And we can build theories to relate these two concepts. That's pretty exciting, but it's manually made. We made it. It took months and years to do. It's not scalable. So what we really got to do, or we'd like to do, is to build systems that can make these discoveries on their own from observations. And this is where agentic reasoning AI comes in. So we're basically teaching these models to look at information, which is sort of measurements of the world and observations, and make connections between them at a very basic level, sort of understand how things are related. And then hopefully we'll make actionable outcomes. So like if you're in healthcare, we might help, AI can help us with administration, automation, to drug discovery. You can discover proteins and molecules and things like this. And so I'll talk about this process in quite some depth, and then we'll show examples and sort of talk about some of the applications, of course. But the beauty of AI today, with even the models that we've seen in the previous presentation we have, is multimodality. And that's really important for science and engineering and tech, or many other areas too. Because if you think about machine learning, maybe in your businesses, in your companies, a lot of times you need perfect data, right? You need a table, basically. You have labeled data. Here's a molecule A, molecule B. These are the properties. The world doesn't look like this, right? It's incomplete. It's imperfect. You might have handwritten notes. You might have a video. You might have interviewed a machinist who worked on a machine for 30 years, and they figured out how to do this really well. So you have all these different modalities, and what we really want to do, we want to integrate all of these modalities, digitize them, tokenize them, and make sense of them and build abstractions. And the key idea, the takeaway from this talk really is going to be, in order for us to do this, we got to build something like Newton's laws. Obviously not Newton's laws again, that might be boring, right? But other fundamental principles that are underlying relationships. And so now you're able to connect principles from biology to art, creativity, to industrial processes, and many more. Right? So that's sort of the promise of this. And we're building this essentially by thinking really deeply about how models work, and not just AI models or machine learning, but any model, right? So a finite element model in your company, or fluid dynamics model, or climate prediction is going to be one like on the left. It has no awareness of its own prediction. You, your company, humans assess the prediction, right? And you decide it's a good prediction, bad, to have a new boundary condition, new measurement. So what we're really going to do is to have models assess their own predictions to have some awareness, in quotation mark, okay? Awareness in the sense that they can assess what they do, they can reason over this, they can correct their own mistakes, they can correct logic, they can make new ideas and new suggestions and sort of iterate through. And this idea, actually it's been around for a long time. In the 60s, including MIT, people have worked on what they called at the time artificial intelligence, of course, and these systems were built sort of hard-coded logic, right? So they try to mimic how intelligence works. And that didn't actually work because they became very brittle. You needed to know everything these systems would do, and that's not how the world works. We have to have autonomous assembly of relationships and understanding. And so this really took, another 60 years or so until we really had agentic models that do not rely on preconceived notions of how these individual components of intelligence interact, but they can self-assemble. Right? And so I'll talk about this in more depth, of course, because self-assembly is fundamental to biology. We study biological materials, and any protein in your body is self-assembled, right? It's not told to assemble in a certain way. It has a memory, an ability to do this naturally. And it's a concerted action that happens, an emergence of properties. And so this is what we're beginning to see with AI. And that's really the direction my lab has taken pretty intensely in the last couple of years, and I'm giving you sort of a story of how we got to this. Okay, so here's an example. Again, for many years, machine learning, AI, you ask the question, you get an answer. Most answers were wrong, and even if they're correct or wrong, the model had no idea, right? I mean, you would ask a regression model, make a prediction about this amazing new molecule, and you had to kind of, is it really true? We don't know. So we built a few years ago when GPT-4 came out, and this was, I think, the first model that sort of had capabilities of thinking about a problem more deeply. We put a bunch of GPT-4 models together and made them work as a group, right? So this was sort of the innovation. We, instead of having one model that you talk to, we had a bunch of AIs talk to each other. And what the model did, we asked the question about creating what we call a force field, which is a kind of description of the relationship between geometry and energy in physics or chemistry. And again, any other AI model, like a graph neural network, would have just made a prediction, and it would have probably been wrong, right? This model understood that it cannot make this prediction because it never seen this data. So what it did instead, it wrote code. It executed the code, and it produced the data by running a DFT simulation, which is the first principles quantum simulation. And so this is pretty exciting. So now, once it had the data from quantum mechanics, it did a regression problem and it fitted this curve, right? And that's the beauty, is that the model really had an ability to make its own data and solve the problem. And so this was kind of like the moment where we really thought, this is really cool, because we want to solve problems in design and understanding, and now we have a tool we can actually build towards this end. So I'll sort of go through a couple of examples to highlight this. And obviously there are too many. I think the time is ticking here, so I'm going to go really quickly. But so there's biology, assembly, collective motions, emergence in ants. They're building bridges. They don't know about bridges. They're building them. Bees can build honeycombs, and proteins can be built with AI now. Is a similar idea. So you can kind of take a bunch of these individual AIs, like a ChatGPT, if you wish, simplistically. It's not actually like this, and you put a bunch of them together, not just 4 or 5, like in the previous example, but hundreds, thousands of them, and they work together on a problem. And this is, of course, something we see in biology all the time, right? We have building blocks that make larger structures. We see this in swarming, right? So not just in ants and honeybees, but in many other phenomena. And so we're building these systems. We're building sort of 2 components here. One is we spend time in our lab building these integrated AI systems that can sort of think and organize themselves. But we also need to build individual models that solve specific tasks. Like, for example, we might want to build an AI model that can design proteins. This is really an expert in protein design, right? Because a general purpose AI today, at least, can't quite do this yet. So you have to train AIs to become very good in specific tasks. We can make AIs that can make graphs, that can understand forces and mechanics and chemistry. So these are special purpose tools, which we're building. And then we're putting them together in groups, right? So now we're building a team. And so we kind of have, so we have a bunch of different components there. We have general purpose AI that can plan. We have AIs that are specialists. And we have even physics simulators. And so that's really the key, right? So now, when a prediction is made, it can actually assess the prediction by running maybe a molecular dynamics simulation or DFT. And if all fails, as you've seen in the initial example, it can even write its own code to run its own simulation. So this is kind of like where the world lies. It's incredibly exciting. We can solve problems we've never imagined being solving, like protein design, and they're physics verified because the model isn't just predicting, it assesses its prediction and improves the prediction. We can do alloy design, so I'm just going to flash through a bunch of examples here. Again, proteins, alloys. We can make scientific discoveries. We've built models that can actually form hypotheses themselves and solve them. So instead of just starting with something you come up with, a problem, the model can actually come up with its own ideas or what it might want to study. And we can do this through what we call graph reasoning. So we can build very large representations of knowledge from papers and books and build graphs that describe the ontologies of how knowledge is organized, essentially. And this can be fed, again, into a solution agent as well. And so now we can do both, formulate the problem and solve the problem. So this is sort of how the future looks like. It's very exciting. This is the swarm example of designing proteins using hundreds of AI agents that each works together on a particular part of the protein. They don't actually know about each other. So we're formulating this as a problem from reinforcement learning, where we're basically just telling the models, each agent, what its actions does for the objective. And the model figures out on its own, each model, how we can best act to make a better outcome. So this is really cool, right? So it kind of really, really fun to think about. And this all, again, is sort of in this picture here, right? So we're looking at relational modeling. We're looking at models that can think. We're looking at isomorphic mapping. So we're forcing models to kind of reflect their own strategies into these shared spaces in which knowledge can be abstracted, from which we can then make much more general solutions. And we're doing this essentially by forcing models to put their thoughts into graphs and symbols. And so those of you who've been around for a long time, you know that this was one of the early ideas in the 1960s, actually, symbolic AI. Again, at that time, the symbolic AI was pre-programmed by humans. Here, the AI learns symbolic abstractions by itself, and it actually does this using what we call reinforcement learning. So instead of teaching the AI the outcome, we're actually letting the AI figure out the right abstractions to get the best possible answer. And we can let the AI kind of do this for many, many days. Here's an example where the AI has been thinking for 5 or 7 days. And it can create a very deep reflection on the world. So again, this is an AI, in this case talking to another AI, where the reasoning steps are used as a way to critique itself, right? And so the AI can kind of bootstrap itself. So this is really kind of where the field is going, and you can really teach models, of course, to become even better at innovating, even better at making connections. And here's sort of how this graph looks like. So this is how the world model built by the AI itself, by basically asking itself questions and reflecting on it and building more abstractions over and over for many, many, many days. And at the end, we see these graphs which actually, and it's surprising, never end, never saturate. So the AI never runs out of ideas. In fact, there's always a reservoir of semantic entropy, meaning capacity to discover new relationships, which are then realized through structural connections. As the AI sees these opportunities, it logically draws connections between these ideas. And so this is sort of how innovation works as well, and also sandpiles, of course. And criticality in physics is a related concept here. So this slide, actually, I think you saw it in the previous presentation. So underlying all of this, of course, is how long can AIs work? So they can work for days, some. But generally, AI systems in agentic frameworks can work for about an hour or two reliably, and you can see this here. And this is a scaling law. I think it's going to be really, really important for this field, as these AIs can work for longer, not just for an hour, day, 2, 3 days, 5 days, years maybe. They're going to become very, very powerful. How do we do this? We build lots of technology to make this happen. We build models. We build inference engines. Everything open source, so everything at MIT we do is open source, so you can access this on GitHub and Hugging Face. We've built inference engines for very large models that we need to serve these large AI systems, of course, on a local computer. We need access to data. One of the things we can do at MIT, and you might have heard about MIT Nano, is an amazing facility where we can actually automate some of those processes in the future. So this is an exciting opportunity here at MIT. You need, of course, have an idea. Of course, you can do a simulation, but sometimes you need to go to the lab at the end, right, and test some of the ideas, collect new data. So this is really how we think the world will look like. It's going to change the world. I think we're not using these AI systems in this way today, obviously. So this is, I think, a study Anthropic did, mostly done for simple office tasks today. Still makes our lives easier, but there's a lot more room, of course, to grow. The expertise you need of your staff is going to change, right? So, in the future, the role of an engineer is going to change. And I'd like to remind us, if you think back, sort of in the 1980s and 90s, so I grew up in the 90s with computers, but if you look back to the 80s when PCs came out, and I've been watching a lot of these sort of historical accounts at that time. If you listen, for example, Computer Chronicles, I don't know how many of you know that. I did not know it, obviously, but I came across it. I was too young. I was like 6 years old at the time. But you can watch it on YouTube. And they discuss PCs, like C64, Apple, MS-DOS, Windows. And they were kind of wondering, what can these things do? They're very brittle. And they were advertising them, kind of like that the guy from Microsoft come in and show the new machine. And it seemed so pedestrian, if you look back at this time. But fascinating. And I think we're in the same point at AI today. These things are very brittle. Lots of questions, and we kind of look sort of ahead a couple of years, and we're going to see some really amazing developments. If you're interested in learning more, I teach classes in professional education, one in June here at MIT on campus, and one in July live virtual, so some of you or your staff want to come. This is obviously a much more in-depth discussion than what I can do in 20 minutes here. Yes, but so with that, yeah, thank you so much. I mean, this, I like to think about this as thinking machines. I've been doing modeling simulation my entire life. In fact, actually almost my entire life, because when I was a kid, I was programming computers to simulate the world. And it's sort of, to me, a dream come true that I have computers can actually think. They can really think and build their own models, write their own code, collect their own data. And yeah, we're using it for some really cool applications. I didn't talk about all the fancy stuff we can do in the application side. I wanted to kind of convey some of the technology and possibilities, but I'm happy to talk about any of the applications. With ILP, I talked to a lot of companies and many others around this. So if you're interested in learning about specific applications and materials and what we can do with it, happy to discuss. Thank you.
So you can read the question first.
So do I have to read the question? So how difficult is it to implement high-level material characteristics like conductivities on all mechanical properties so that they can be predicted by model? Well, so you need some observations. And if you were to go with an AI model that has no idea about any kind of mechanical properties, you traditionally do like a regression model. You need a whole ton of data. Now, if you're starting with these agentic AIs, they have some understanding usually about the problem at hand. So they know something about mechanics. They know something about connectivity. So the way we're approaching this is by using models that we call pre-trained. They understand something about the world. And then they learn. They can learn from papers, scientific literature. They can learn from simulations. They can learn from experimentation. And oftentimes, we need very little data, or because these models are trained using reinforcement processes, we can also teach them to make better predictions by letting them basically fail. And that's the point, right? You want the models to make prediction, do reasoning, and make a mistake. And then the models will have to figure out a pathway to make better predictions. So all of this is, and I think I went through this very quickly, but is that we're really trying very hard to make models not remember the answer. We're encouraging the model very strongly to understand and learn the path to get the answer. And we're doing this through symbolic abstraction. So models in the reasoning steps are not allowed to just remember the answer. They can if it's trivial, but we're making it really hard for them. So we're penalizing them for this. And so, in a way, yeah, it's like you want to find these hidden laws, these hidden Newton's laws. It doesn't have to be quite at the level of Newton's laws, but these relationships that are foundational to describing your properties. And so you can get away with reasonably little data. So that's a real game changer. So to traditional machine learning, of course, yeah. Another question, how would you validate? Yeah, so you validate it in you can give different reward functions, right? So one could be, let's say you're designing a protein. I mean, it could be the patient response, right? And that could be your final outcome. But usually you have intermediate steps. Like, for example, you want activity, you want stability, and you want to get something like, you want to get proteins that are stable and that are active. And ultimately, the reward will be, does it actually work in a patient? So I would say, there's different levels. And the beauty of these agentic models is exactly that they can do this. You're not limited to one thing. You're not training models to have one outcome that you know. In fact, what we find in these agentic systems is that they will define their own intermediate steps. So they will say, I have to design a protein. Okay, I don't know the answer to this problem. Let me find a path to get to that answer. And they will actually define their own merit. So they might make a plot, and they might analyze the plot. I didn't really get to this either, but the design of what validation looks like could be part of what the agents can do on their own. Now, that being said, you're not out of a job yet. No, I'm kidding. Especially if you're here, you're in the right place. And but we can supervise this process, of course. And there are human interventions we can have. We can say, okay, here's an intermediate result. How does it look like? And we do this all the time. And then you say, okay, I like it, but I don't like this. I like the general direction, but I don't like this chemistry because it's actually toxic, right? And so we can give this feedback to the model, of course. So you are one of the team members, if you wish, in the agentic AI system. And we're building these in, of course, because there's a lot of human domain expertise, of course, that we don't want to, get rid of. Yeah.
Thank you very much.
Thank you so much.
Professor
Thank you so much.
Buehler.